First problem, you're expanding this deal, so make sure you show the expansion in terms of the factors. Of course, you're finding these things up here, right? So make sure you show that expansion. And then, well, let's see, I called this K0, so I'm going to give you these answers. K1. So K0 you find by multiplying both S, and you should get 1/6. Good. K1 you find by multiplying both sides by S plus 2. Then you should get -1/2. So far, so good. And then K2 from multiplying both sides by S plus 3. And I got 1/3. Check. So then you stick those numbers up there, and then you do the inverse Laplace. So this one turns into the unit step. See, K0 is 1/6, you got to multiply that. And then this becomes e to the minus 2t times K1. Because the 2 goes in there. And then you get K2 is 1/3. E to the minus 3t. And if somebody said, is this system stable? What would you say? You look at the real part of the roots. We got -2 and -3 are the roots. So it's stable. Is it oscillatory? No imaginary parts. What about this root? That's a root at 0. But that doesn't come from the homogeneous solution. This is the forced solution. So when you're looking at stability, you don't look at the forcing function, because the forcing function can be anything you want. It could be all kinds of forces. So for stability, you only look at the homogeneous or the transient solution. So even though we have no idea what the system is or where the differential equation was that this came from, all we're given is that this is the thing that you get when you apply the differential equation and you solve. We can still look at it and say, oh yeah, it's stable, and that this was the forcing function here because that's the steady state solution. So make sure you show the work on this. I've given you the answer, so we're going to grade the work, of course. How about the next one? So we've got so we talked a little bit about this, right, last time, but we didn't go through an example. But in the handout, it shows you how to do this. But I'll show you again. I hope you guys read the handout and gave this a shot. So you have to expand this into an s plus 1 factor and an s plus 1 squared factor. Because otherwise you don't get, when you add them back up, go in the other direction, it doesn't work. It's just that you just have to know that that's how you have to get it to work. And notice I've numbered these to match, kind of match the roots. So I put a 3 here and I put the 3 over that. It's just easier to keep track of. You don't have to do that. And so we can find A2. If you multiply both sides by the whole thing down here, then you get 10 over s plus 3 equals s plus 1 times A1 plus A2 plus s plus 1 squared times K3 over, right? Just multiply by that whole thing. And that cancels out, that's there. So if you let S go to -1, knocks that out, so you can get A2 really easy, just the standard method. That's for the highest power one. So you should get A2 as 5. And then you can get why did I call that K? I don't know. You get K3 the same way. You can multiply both sides by S plus 3, and everything's good. And let S go to -3, and you get 2.5. But when you go to get this one, we're multiplying by S plus 1. And what do we get for that? So we're going for A1 now over here. So multiply both sides by S plus 1, and you get 10 over S plus 1. There's still part of that there. Looking good so far. There's A1 all by itself. Right, and that's going to look good. We're going to let S approach -1. It's going to knock that out. Oh, but what happens when S goes to -1 here? Oh, wait, sorry, we canceled out one of those, right? This is going to go to infinity, and we don't get anything. So we're stuck. The handout shows you a way where you multiply by S plus 1 squared. And then take the derivative. So there's one method is multiply by S plus 1 squared, and then take d by ds of both sides of the whole thing, and that knocks this term out. So if we look at this thing where we multiply both sides by S plus 1 squared, we got that, right? That was a step up here, so it's the same step here. But then if you take the derivative, A2 is a constant, so it goes away. This still gets knocked out when S is -1, and the derivative here gives you A1 all by itself. So let's start with that. So we still did the same step, multiply by S plus 1 squared. So now we're finding A1. So we multiply by S plus 1 squared, and then we're going to take d by ds. So we're going to get 10 over S plus 3 to the -2. All right, so that's S plus 3 to the -1 up here. Take the derivative, and we get that. Derivative here gives us A1. A2 is 0 because the derivative of a constant, and we're still going to get an S plus 1. We take the derivative of that. And then if we let S go to -1, that gets knocked out, and we get A1. But then, that requires you to think a lot, doesn't it? And figure it out. Which, if you get good at this, you can do that. But another way to do this is to multiply both sides by the whole deal. So let's go over to the other board to do that. So this homework, going over the homework, is a little bit of a lecture and a little bit of showing you the answers, but that's okay. You gave it a shot. So you multiply the whole thing by that, and we're going to get 10. And then we get A1, had the S plus 1 at the bottom, so we get an S plus 1 times an S plus, multiplying through by the whole left-hand side, the bottom. Did that one, and then we get A2 and the s plus 1 squared knocks out part of the denominator, so we get that. The s plus 3 knocks that out, so we're left with that. So far, so good. And then we need to multiply everything out. So we're going to get s squared from over here times a3. So I collect all those together. And then we're going to get a 1 times s and a 3 times s times a1. And we're going to get an a2 times s, and we're going to get an a3 times 2s in here. So when you do all that algebra, you end up with that multiplies s. You're going, this is a lot of work. Yeah, it is. And then we're going to get a bunch of constant terms that come from a3 times 1, and a2 times 3, and a1 times 1 times 3. And then you equate equal powers of s, because you're saying the polynomial over here has to equal the polynomial over there. And so that looks like a lot of work, because then we end up with 3 equations and 3 unknowns. You can solve for a1, a2, and a3 that way, which is real straightforward. Either way, 2.5 for a3, and then a minus 2.5. And you could, the stuff on the other board over there gives these same answers. It's just different ways to do it. What I did was a hybrid approach. I found the 2 ones that were easy to do without the derivative with the normal method. And then I already knew A2 and A3, and then I stuffed them into this to get A1. So it's a matter of just kind of poking at the problem and finding the easiest path to the solution. You're welcome to do it any way you want. This is probably the most straightforward way, because you just multiply and then you equate and you solve. But it takes a little bit more work. So are we good on that? So you probably need to go back and work on that a bit if you didn't get all the way through it and you got stuck on that other term. So make sure you complete that. And I'm still getting mixed messages as to whether you guys have done this before. Some of you say, yeah, we did this in differential equations, and some of you say no. You've seen this before? Some, a little bit. Maybe it depends on where you took differential equations. But make sure you go through the handouts in there, because that gives you additional examples that are a part of what I'm doing here. Okay, so the last problem, let me switch. Over here, you got the differential equation. Initial conditions are 0, so when you Laplace, you should get the right-hand side had e to the minus 2t. And you just look that up in the tables. So did you guys get that? Again, we're just using the definition. Go to that table that has how to do derivatives, right? Just like the example we did in class. So you're good there. So make sure you show that work. Show the solving for f of s. So you get a polynomial, and then you factor it into those roots, which is what you have to do. And then you do the partial fraction expansion. So make sure you show the work for that. So you should get this, check your answer. So you should get the constant over the s plus 4 is 1/6, 1/3 here, minus 1/2 there. And then you inverse Laplace. This is e to the minus 4t, e to the minus t, e to the minus 2t. And you're done. And again, how about stability? We look at this, e to the minus 4t, e to the minus t, e to the minus 2t. All of those are going to go to 0. But if that's all we wanted to do, all we had to do was do this and stop. Because then we look at the roots. The roots are minus 4, minus 1, and minus 2. Those roots go here. And you know that the roots are negative and they're real, so it's stable but non-oscillatory. And that's what some people call a math shortcut, but really it's a matter of having done these enough that you know the answer from this point forward, so you just know what the answer is going to be because you've done it so many times. So now I'm going to show you an even faster way to do these problems. You want to know? So in MATLAB, everything that you ever wanted to do as far as math is pretty much programmed in there. So there is a function in there, a method. It essentially calls a program that does this, and it does partial fraction expansion for you. So I'm going to show you real quick how to do that. And what I'm going to do is I'll give you 2 points extra credit if you turn in a MATLAB session printout doing this, where you check your answers. All right, sound good? So 2 points extra credit, because I didn't ask you to do this, but I'm going to show you for doing the MATLAB. So print out and turn in your MATLAB session. I guess you're turning this in online, so really all you have to do is do a screenshot of it and attach that to your PDF, and you're good. Yeah, I don't know how to do that, but if you know how to do it. So you're going to program it into, you're going to type the commands into a .m file and then just execute that? Yeah, that's fine. Yeah. So you can save the .m file as a PDF. And yeah, that's fine. Because the output's going to show up in the command window when you run it. All right, so here's how you do this. It's using the symbolic manipulation toolbox, which is probably what Maple does as well. And do you know how to do this in Maple? Yeah, all you got to do is Google search it and it will show you, right? That's how you find it out. So in MATLAB, you have to tell it that the S thing that you're going to be typing is a symbol, not a number. So you say sims S. And that now in your MATLAB session, it says, okay, every time you type the letter S, it's going to be a symbol, and I'm going to work algebra on the symbol. And so then the function, you say part frac, and inside the parentheses, we're going to give it the function that we want it to inverse Laplace. And so you have to be a little careful here with your parentheses. I'm going to do the first homework problem, which was 1 over s times s plus 2 times s plus 3. So I do 1 over s times s plus 1 times s, need my parentheses, s plus 2. Sorry, 3. Did I get that right? I'm looking at two different things here. 1 over s times s plus 2 times s plus 3. Is that what I got? No. And then I got to close my parentheses on the 1 over thing. And then I got to close it on the partial fraction expansion function. Yeah, so it's 1 over the quantity s times s plus 2 times s plus 3. And it'll tell me if I botched it up. And there's the partial fraction expansion. So why do we do this by hand? So you can do this for the second problem, which is 10 over s plus 1 times s plus 4 times s plus 3. Close the parentheses on the denominator. And on the function, let me double check I typed that in right. That's not even close. What am I doing? It's s plus 1 squared. Gosh, I was looking at the wrong line for sure. It's 10 over s plus 1 squared times s plus 3. Okay, I finally got it together here. Close the denominator, close the function, and there's the partial fraction expansion. Pretty easy. So why do we do this by hand? I have several philosophies. It's like, why? Because we can do this, right? Yeah, okay, for the quiz, you're not going to have a computer. I think it's important to understand whenever you're using software what it's doing, because you need to know that what this thing is doing is what you really want it to do, because you're just calling a function. And you might want to check it by hand to make sure that the software is doing the right thing. I always have a deserted island mentality. It's crazy, but I used to watch Gilligan's Island, right? So if you were stranded on a deserted island and you had to do partial fraction expansion, you could do it, right? You never know. It's probably not going to happen, but you never know. But again, the real reason is it's important as an engineer and a scientist to understand what's going on behind the software, because there's always limitations in what it's doing. All right, so that's an easy way to check your answers and know whether you got them right or not. Yeah, if you copied and pasted what I just did here, the commands and the answers, into your PDF, you're fine. 1, 2, and 3. Yeah, just do them all. So, yeah. Mm-hmm. Anything going on in the chat? I don't know what they're talking about. Windows Shift S. Okay, so last time we were talking about the mass spring damper system and different values of B. So I'm going to finish that up. And then I'm going to do another example where we have complex roots to show you how to handle that, and we'll be good there. Am I over there or over here? So if you figure out how to do this, you're talking in Maple, right? Or did you say Mathematica? Maple? You figured that out, I'll let you give us a lecture on it on Friday. Oh, just if you show me, I'll look at your printout and maybe I'll show it in class how to do it. I'm sure it is, and I know Dr. Gang uses that a lot in stuff he does, and it's really powerful. Okay, so we were looking at the mass damper system. And we had, originally the damping was 12 and K was 25, and we got these roots. And we look at them and we say they're real and they're negative, so it's stable and non-oscillatory. And then we said, okay, what if B is 6? And then we said, okay, when B is 6, we get a negative real part, so it's damped and stable. But we have an imaginary part, so it oscillates as it damps out with a frequency of 4. So we know that. How about when B is 10? So we could do that. Plug in 10 in that polynomial, find the roots, and we get those real roots. And then we plug in B equals 9 minus 4.5 plus 2.17 I. And we're saying, hey, when we change B, obviously it changes the roots and it changes the stability. So how does B really affect the stability? It'd be nice to do a plot of the roots on the complex plane as B varies. And so we can do that. Let's make a over here. So here's the imaginary part. Here's the real part. Let's see, B is 12. We have minus 2.683 and close to 10. So I'm going to have to put marks here too. Right? And I'm going to need marks up here. So this is going to be 2, 4, 6. So when B was 12, I got minus 2.683. So that's somewhere like that. And minus 9.37. So I'm over here. And that's a real good visual representation. It's damped. It's non-oscillatory because they're all on the real axis. Okay, how about B equal 10? Got minus 5 and minus 5. So there's 2 of them right on top of each other here. And then 9 is minus 4.5 plus or minus 2.17. So then we're up here. And we're down here. And then 6 is at minus 3 plus or minus 4. And so you can look at that and say, oh, this is a design tool for picking B for my system. And it's called a root locus plot. Which is a plot of the roots as some parameter varies. In our case, it's B. So then the question is, well, what do we want our system to do? If I want my system to oscillate with a frequency of 4, I look at this and I go, I need to pick B to be 6. And I've designed my system. I've picked my damper and my spring, and I know that the system will oscillate with that frequency, and it will damp out. If I don't want it to oscillate at all, then I could pick B values that are these roots along the axis here. And in fact, an optimal point is when both of them are the same, because if I'm past that, like if I'm at the 12, this one's really damped with a -10, so it dies off really fast, but this one lingers around longer because it's only e to the -2t, which dies off slower than this one here. So this is, we can even identify this kind of optimal, or what's called critically damped point, where this is the best damping relative to the spring that you can get. Because if you get any smaller than that, too much damping, it's called overdamped. You get here, it's critically damped, and then it's underdamped when it starts oscillating. So a root locus plot is a design tool for picking a parameter. And often for an aircraft, people will do root locus plots related to CM alpha, the pitch stability. And they'll vary the pitch stability to find the optimal point where they get really good damping, but no oscillation, or maybe minimal oscillation, or low frequency oscillation. So that's another tool that's available to us with the Laplace transform method of solving differential equations. All right, one last note about Laplace transforms. What happens if you get these complex roots, and what's the best way to handle the partial fraction expansion? So as an example, let's say we get this. So in fact, this is a B of 6 and a K of 25, which is what we've already done. And we know we get this set of roots here, 3 plus or minus 4. So this thing is going to be S times S plus 3 plus 4i and S plus 3 minus 4i. Those are the two roots. We're going to factor it into that thing, and we expand it, and we're going to get and then you multiply both sides by S and let S go to 0, and you find that one. You multiply both sides by this thing here, let S go to minus 3 minus 4i. That sounds like it's going to be a little bit of algebra, doesn't it? You got to keep track of the real parts and the imaginary parts. Same deal for this. And you can do that, and you'll get the correct answer. But there's a better way, is to just expand it in terms of, in other words, you leave that second order term here altogether, and you expand it like this. And the rule here is that the denominator that you put over a polynomial always has to be one less order than the denominator. So if we have that S squared down there, we got to have an S in the top. Otherwise it doesn't work. And I'll show you why in a minute. If we say, oh, let's just stick A up here, I'll show you why it doesn't work. So if you get complex roots, the rule is leave it in the second order polynomial form. And you can look this up in the Laplace transform tables because people use this all the time. So this is in the tables, just like the e to the at stuff. So how do you find these? Well, we do the method where we multiply both sides by the whole thing and then equate equal powers of s. So we're going to do that. So we're going to multiply that whole thing. So we're going to get 25 is equal to k1 s squared plus 6s plus 25. We're looking at that there, and then we're going to get a plus bs times s, because the other stuff gets knocked out. Following? Just multiply and cancel stuff out. And we have to get all our powers of s together here. We're going to get k1 times s squared and b times s squared. And then our s's are going to come from a times s and k1 6s. Then the constant term, all we got is 25 times k. And so we equate equal powers of s. Looks like this stuff is going to be equal to 0 because there's no s squared term over there. This stuff's going to equal 0 because there's no s. And this thing's going to equal 25. So those are the three equations we get. We get 25 equals 25 A1. Well, that one's easy. A1 is 1. K1, yes. And then we get 0 is equal to E, and we get 0 is equal to A plus K1 times 6. And we already know K1, so that means A is going to be equal to minus 1/6. Did I do my algebra right? No, I divided. Shouldn't have done that. K1 is 1. Yep, okay. And then the other equation is A plus K. We already did that one. Yeah, so that gives me A, and then K1 in here gives me B is minus 1. So that's how you could do it and keep it all together. And then you've got the expansion. Nice. X of S is 1 for S because K1 was 1. And then you can look this one up in the tables. And this is a little bit of work. How much time do we have left? 6 minutes. I think we can do this. So if you look this up in the tables, you'll find this one. What we need is a thing that has S squared on the bottom and S on the top. And if you look through that, you'll find this. And when you're looking these up, that's what you look for is the S's. Don't worry about the constants and everything else flying around. You say, I need an S squared polynomial in the bottom and an S polynomial in the top. If you look at the tables in the handout, this is the second one from the bottom. So we looked that up, and what we have to do is now match stuff in the tables to what we actually have. So we start matching. Well, it's pretty clear alpha is 6, right? Let me make sure I wrote that right. Yeah, okay. So what is omega n? Because that's the next one that's usually easy to get, because omega n squared is there and 25 is there. But how about the thing that multiplies up here? Seems like we're stuck. Omega n squared is 25, but it's also 1. Well, let's try 25. Then what do we do about this one here? Well, that one we can fix up because it's just multiplying it by a constant. So what I need to do is write this as 5 squared over 25. And then I look this up in the tables. And you go, well, that's kind of difficult. Why did they do that? Well, this fits all possible s's and s squareds, and then you just fiddle around with what you have until you match it up, and then the table gives you the answer. That's what you're doing. So that means omega n is 5, and then how do I find this one? 2 times the zeta times omega n has to match up with the 6. So you're doing intelligent pattern matching like you're taking the ACT test or something like that. And that's the process mentally that I recommend, is you match up the numerator, and then you match up this one, and then that's going to give you this here, and then you fix up any constants outside. Because you can always multiply and divide and pull stuff out of the Laplace, because those constants can come in and out of the Laplace. So you look this up on the table, and I think we're going to have to finish this next time, but let me show it to you. So these are the Laplace transform tables. These are the easy ones. You go down to the second page. I don't see any s's. There's an s on the numerator, but no s times s plus something. So I keep going, keep going, keep going. And there's the one I picked out right here, because it matches both the numerator and the denominator. But this looks pretty complicated, doesn't it? But it's not really that bad, because all you're doing is putting the numbers that we just found into that thing, and then you have your answer. So we'll do that next time. Oh, I'm looking at the wrong one. Sorry. This is the match, right? And then this thing here. So it's going to take a little bit of time. We've got to plug in alpha here and alpha there and zeta here and omega n, but it's just plugging numbers and doing algebra. And believe me, this is faster than going and doing the complex number expansion like this and trying to keep track of the real and imaginary parts, because you're guaranteed to make a mistake if you do that. All right, so remind me, we need to wrap that up on Monday or on Friday. And quiz, normal procedure on quiz with your normal rooms that are assigned.